Hello everyone, welcome back to Medical Physics Academy. Today I'm going to talk about positron annihilation experiment. In this experiment I set out to detect gamma emissions from positron annihilation and understand what those tiny flashes of light can tell us about matter, energy, and even medical imaging. By using a sodium-22 source and a dual detector setup, I was able to explore time coincidence, energy calibration, and angular correlation of 511 keV gamma photons. Here's how I did it and why it matters. Let's start with the radioactive source, sodium-22. It decays into neon-22 either through positron emission or electron capture, with a half-life of about 2.6 years. Now, when sodium-22 emits a positron, it also leaves the neon nucleus in an excited state. This excited nucleus immediately releases a 1274 keV gamma photons, almost instantly in about 3 picoseconds. That emission gives us a precise time reference for when the positron was born. After that, the positron travels just a few millimeters before it finds an electron to annihilate with, usually within 10 nanoseconds. And that annihilation, it produces two 511 keV gamma photons, flying off in almost exactly opposite directions. These twin photons are the key to everything we measure. This process isn't just fascinating, it's also incredibly useful. In medical imaging, specifically PET scans, the timing and direction of those 511 keV photons are used to reconstruct images of what's happening inside the body. The positron's lifetime before annihilation can even reflect tissue density, oxygenation, or pathology. And beyond healthcare, this physics is applied in material science, radiation monitoring, and industrial systems. Now, let's talk about the setup. I placed the sodium-22 source at the center of a detection system, two NAITI scintillation detectors, each coupled to a photomultiplier tube. The photomultiplier tube PMTs were powered with high voltage under 1000 volts supplied by an Ortec 556. Signals from the detectors were routed through amplifiers to shape the pulses and then sent to a time-to-amplitude converter or TAC. From there, they went to a multi-channel analyzer or MCA, where we could view and record the energy spectrum. Using Amtech software, I was able to visualize the entire gamma spectrum in real time. Right away, two distinct peaks appeared. One at 511 keV and another at 1274 keV. The 511 keV peak was taller because every single positron annihilation creates two of them. The 1274 keV peak is smaller, since it's emitted in only about 90% of the case. What's especially important is that the peaks were clearly separated. That clarity tells us our detector resolution was solid, thanks to the photomultiplier tube stability, the quality of the scintillator crystals, and the amplifier settings. Each histogram peak shows the number of gamma photons detected at a given energy. The better the resolution, the easier it is to isolate and analyze specific interactions. To ensure accurate measurements, the energy readings were carefully calibrated to voltage. An Ortec 480 pulsar was used to generate test pulses at 2, 4, 6, and 8 volts. These were confirmed on an oscilloscope and then passed through the MCA to establish the relationship between voltage and the photon energy. Once calibration was complete, the pulsar was disconnected and attention shifted to the 511 keV signal from detector 1. The amplifier gain was adjusted so that the 511 keV peak aligned with 6 volts. The MCA was then connected to the single channel analyzer or SCA. The SCA lower level was set to 4.64 with a window width of 0.121 to isolate the 511 keV events. The same procedure was then applied to detector 2. This first part of the experiment demonstrated the fundamental physics of positron annihilation and gamma emission. By capturing and analyzing the energy spectrum, identifying both the 511 and 1274 keV peaks, and calibrating the system with care, a solid foundation was established for more advanced measurements. Part 2 will expand on this setup to investigate timing coincidences and angular correlation between the two 511 keV photons. These measurements are essential for understanding symmetry principles, conservation laws, and the operational mechanics behind PET imaging. Thank you and stay tuned.